Hello everyone and welcome back to the C++ 3D game tutorial series. In this 38th video tutorial, we will see how to make a 3D ocean. In particular, we will see how to generate the ocean mesh, how to render the water surface through the vertex shader and the height map, and in the end, we will see how to enlighten and color our ocean. As always, we will face three main parts: requirements, design, and implementation of all the necessary things to make a 3D ocean. Let's start with the requirements. We need a C++ IDE. In this series we use Visual Studio 2019 Community. The target platform is Windows. The target graphics API is DirectX 11, and last but not least, a bit of knowledge of C++ programming language is recommended. Now we can start the design part. In order to create our 3D ocean, we have to face four main phases, like we have already done with the terrain: the generation of the ocean mesh, the rendering of the water surface through the vertex shader and the height map, the computing of normals through the height map, and in the end, the coloring of the surface of the ocean. We have practically faced all the first three phases in the previous tutorial. Today, we will focus mainly on the coloring of the surface of the ocean. As first thing, we should use a waves height map, that unlike the terrain height map, it contains the height values of a series of waves. Then, we have to tile the entire ocean mesh with the same waves height map multiple times, like in these images. And here is the final result. Unfortunately, this is not enough, for the waves should change in some way. To create such effect, we should translate the text code in some direction, through this formula. But how can we make a translation inside the shader? Through a variable that changes continuously during the execution of the game. We can call this variable time, and we can compute it as the sum of the delta time values at each game loop iteration. In the end, we pass it to the shader through our constant structure. And here is the final effect, in which we have the waves that move along a specific direction. Unfortunately, that's not good enough yet. The waves seem to be motionless. To make the effect a bit more dynamic, we could compute a further text code that changes along another direction with respect to the previous one, like in this code snippet. Once we have two different text codes, we fetch two different pixels from the height map, and then we can mix them through a linear interpolation. We should get a result like this one. This is surely a better effect than the previous one. Another important topic to face to improve the quality of our ocean is the alpha blending. What is the alpha blending? In a very few words, alpha blending is the process of combining one image with a background to create the appearance of partial or full transparency. In our case, this feature allows us to render partially or fully transparent 2D or 3D meshes. With such feature at our disposal, we can make the surface of our ocean transparent, obtaining in this way the final result. If you have questions, doubts, or comments about this topic, don't hesitate to leave them in the comment section of this video or in the Discord server. The link to the Discord server is available in the video description. Also, if you find these tutorials helpful, please consider to support their development on Patreon. Every single contribution makes the difference, regardless the amount. Very well, we have gathered all the necessary information to start the implementation. As first thing, let's go to the shader folder and let's rename my material.hlsl file in base.hlsl. Then we have to improve the way in which we handle the shaders. In particular, we have to move the common data structures and functions of the various shaders in a suitable file that we can call common.hlsl file. Let's take them from the terrain.hlsl file. At this point, we have to include the just created common file in the other shaders in order to include the common structures and functions easily. Let's don't forget to remove the structures we have just moved in the common file. So far, so good. Unfortunately, the include feature of HLSL doesn't work automatically and immediately. We have to create a class that handles this specific case on our own. To do that, let's go to the source and graphics folders and let's create another file. Let's call it shader include. At this point, let's create the shader include class. The first thing to do is to add a file system path, in which we will store the path of the shader we will have to compile. Then we have to transform this class in order to be usable by the d3d compile function. This can be done by extend this class from the id3d include interface. Let's go to its definition and let's copy its two methods signatures, open and close, inside our own class. Let's modify them a little bit. The open function is used by the d3d compile function to retrieve the data of the included file defined in the file name parameter. So our goal here is to find a way to open the included file, retrieve and store its content in a sort of array, return it to the d3d compile function. So, as first thing, we have to create the path of the included shader. That is the concatenation between the shader path we are currently compiling and the included shader file name. Here we are presuming that the included shader file name is a relative path. Then we simply open our file through the standard C++ fstream. If the file has been opened, let's retrieve the content of our shader file in form of a string through the string stream class. That's not enough, though. We have to be sure that the data content of the file survives to the shader include object destruction. This can be done by allocating a char array in the heap. In the end, let's call the memcopy function to copy the content of the string to the just allocated array. At this point we have to do nothing but close the file stream and pass the pointer to the allocated array to the data parameter, and the length of the file content to the bytes parameter. If everything is going well, let's return as OK, otherwise let's return as false. Last but not least, in the close function we have to simply call a delete function in order to deallocate the array passed through the data parameter. At this point, let's return as OK. That's all. Now we can go to the vertex shader.c++ file, and here let's include our shader include class. In order to locate the file, we have to go to the project properties, and in the VC++ directories tab, we have to add a further directory in the include directories field. That is our source directory. Let's create the shader include object. Let's pass the shader path as parameter. And in the end, let's pass a reference to this object in the d3d compile from file function. Very well, let's do exactly the same thing in the pixel shader class. Let's see if it works. And it works. What's next? Well, let's add a further data structure in the common shader, and let's call it camera data. Here, let's move the view and projection matrices and the camera position. Let's add it to the constant structure. And in the end, let's use the camera object in the various shaders. Last but not least, let's update the C++ counterpart. So far so good, finally we have prepared all the necessary things to start the implementation of our 3D ocean. So let's go to the entity folder and let's start to create the water component class. Let's add a constructor and virtual destructor as usual. Let's extend this class from the component class. Then let's override the onCreateInternal method, and as we have already done with the other components, let's try to add this component to the graphics engine. Good! Now let's go to the graphics engine class and as usual let's add a set of water components. Let's manage the water component in the add and remove component methods. Very well. The next step to do is to implement the water component. Most of the features has been already introduced through the terrain component, so we have to do nothing but to replicate what we have already done in the previous tutorial. As first thing, let's copy the attributes of the terrain component. Let's change them in order to be used for the water component class. Let's also copy and paste the various setter and getter methods. At this point, let's reuse the generate mesh function. Let's remember to change the shader from terrain.hlsl to water.hlsl. Let's also copy and paste the update data function. So far so good, let's finally create the water shader. Then, let's copy and paste the content of the terrain shader in the water shader. At this point, let's go to the common shader file and let's create the water data structure with the same attributes of the terrain data structure. Obviously, let's add it to the constant structure and let's call it water. Then, let's come back to the water shader and let's start to replace the terrain with water. In the end, to test it immediately, let's simply change the color of the ground in a blue color and of the cliff color in a white color. The shader should be ready. Let's go to the graphics engine C++ file and in the update function, let's copy the same procedure adopted for the rendering of the terrain and let's paste it at the end of the update function. We place it at the end of the function in order to apply correctly the alpha blending. We will see that in few moments. For now, let's simply replace the reference to the terrain components with the water ones. Last but not least, let's go to my game C++ file and in the onCreate method, let's add a new entity for the C. Let's remember to include the water component in the old header file. The only resource to set here is the wave's height map. Let's also create and load the wave height map texture. In order to center the terrain, let's translate our C entity. Don't forget to replace the terrain references with the water ones in the graphics engine C++ file. Let's see if it works. And it works! The next step to face is to furtherly separate the common procedures across the various shaders, like the computing of the phone lighting. So let's go to the common shader and let's start to implement the compute phone lighting function. We can retrieve the implementation of this function from the terrain shader. At this point, let's add all the necessary parameters, in the order camera data, light data, the word position of the vertex, the word normal of the vertex, the various numeric constants of the phone lighting, like Ka and Ia for ambient lighting, Kd and Id for the diffuse lighting, and Ks, Is, and shininess for the specular lighting. Let's simply adapt the code accordingly. Very well, what else? Well, let's replace the computing of font lighting in the various shaders with the new function. Good, let's see if it works. And it works. The next thing to do is to transform even the computation of normal from the height map in a function, as we have already done with the font lighting. Here, let's be sure to negate the x and z values in order to handle correctly their direction of light. Let's use the compute normal from height in the terrain shader. Don't forget to go to my game C++ file and in the onUpdate method, let's make a positive x value when we set the rotation of our light entity. Let's see if it works, and it works. At this point, let's use the compute normal from height in the water shader. So far, so good. Let's make the things a bit more interesting. Let's enable the specular lighting of the water. Here we go. Let's stop the animation for now. Good. What can we do now? Well, let's fix a bit the code of the water shader. For example, let's rename ground and cliff with watercolor and creased color. For the watercolor, let's use a light bluish color. And for the crest of the waves, let's use a simple white color. Let's replace those new variables in the code. Let's see the result. Cool, now the flat mesh starts to seem a real sea. Obviously, there are other things to do yet. So let's start to create the movement of the waves that we have faced during the introduction. As first thing, let's go to the common shader and in the constant structure, let's add a float time variable. Then let's use the formula seen previously to compute the text code in order to make the animation. So let's multiply the text code retrieved from the vertex buffer by 8 and then let's translate it along both the x and y axes. This can be done by summing the time multiplied by a very little value, in order to slow down the speed of translation. At this point, we have to concretely define the time variable in the graphics engine C++ file. And compute it in the game C++ file, in the same way we have already seen in the introduction. Let's pass the total time variable to the constant data structure. And let's finally see if it works. And it works, but as we know, in this case the waves seem motionless. To improve this effect, let's go to the water shader and let's compute a further text code, for which we can fetch a further pixel and so a further normal, and then we can mix it, or better said, linear interpolate it with our first normal. And here is the result. Now the effect is surely more dynamic. As we can see here, the C changes at pixel level, but not at vertex level. Let's solve this issue by making the linear interpolation between two height values even in the vertex shader, and let's displace our vertices. Let's see if it works. And it works. Now the vertices of the mesh change their position continuously. What else? Well, the last part to face is the application of the alpha blending. So let's go to the render system class and let's add a D3D11 blend state smart pointer. Let's call it alpha blend state. Then in the init rasterizer states method, let's create a D3D11 blend state descriptor. And let's initialize its values. For now, let's limit ourselves to use the values shown on the screen. We will deepen the alpha blending topic in the next tutorials. In the end, let's create the blend state by calling the createBlendState method. For simplicity, let's also bind this blend state to the graphics pipeline only one time here. We will improve this aspect later. For now, let's go to the water shader and let's apply an alpha value of 0.8 in the returned color. Let's see if it works. And it works! We see through the surface of our sea. There is only an ugly effect here. That is the floor of the terrain. There are a lot of ways to solve this issue. Let's go to the terrain shader and let's use a simple approach in which if the height of the terrain is 0, then let's make it completely transparent, otherwise completely opaque. Let's also remember that if we make the terrain transparent, we have to place the rendering code of the terrain after the other objects. In such a way, it is possible to blend the color of the surface of our transparent objects, in this case only the terrain and water objects, with the opaque objects that should be rendered in the background. Let's see if it works. And it works! So let's only tune a bit the shininess of our water shader. Here we go! That's all for now, folks. Today we have seen how to create a 3D ocean. The next time we will see how to create the fog. I hope you enjoyed this video. See you soon. Thanks for watching.